Welcome to my channel. Today we are going to discuss about the objective type question from the topic of fast Fourier transform, that is FFT. In that FFT there are two algorithms there already, you know, the DIT algorithm and DIF algorithm. So from that algorithm we are going to see the questions. So the first question, FFT may be used to calculate DFT, IDFT. IDFT means inverse DFT. Direct is a transform, indirect is a transform. FFT may be used to calculate the DFT of the given sequence and IDFT of the given capital X of K. Using FFT, we can't find the Z transform and indirect Z transform. So 1 and 2 is the correct answer. Okay, 1 and 2 is correct. Then the next one, the Cooley-Turkey algorithm of FFT is a divide and conquer algorithm, divide and rule algorithm, split and rule algorithm, split and combine algorithm. So this algorithm, it is called as a divide and conquer algorithm. So here the input sequence are breaking into two sequences and we are performing the DFT, then we are combining. Okay, so that's why this algorithm, it is called as a divide and conquer algorithm. The divide and conquer approach is based on the decomposition of endpoint DFT into successively smaller DFTs. This basic approach leads to FFT algorithm. This is true or not true? Okay, so in divide and conquer approach, the endpoint DFT, that is for example, the 16-point DFT is divided into two 8-point DFT, and each 8-point DFT is divided into two 4-point DFT, and 4-point DFT is divided into two 2-point DFT. So and finally we are combining. So that is that process is used in FFT algorithm. It's a true only. The next thing, if we split the n data sequence into two n by 2 data sequences, f1 of n and f2 of n, corresponding to even numbered and odd numbered samples of x of n, then such an FFT algorithm is known as decimation in time algorithm, that is DIT algorithm. It's a true. Okay, so in DIT algorithm, if we want to perform endpoint DFT means we will have the x of n is equal to 8 samples. In that 8 sample, we are splitting odd numbered, odd indexed sequences separately, even indexed sequences separately. That is x of 0, x of 2, x of 4, x of 6 we are taking. It's a even numbered sequence. Odd numbered sequences x of 1, 3, 5, 7 and we are performing n by 2 point DFT, then we are combining the answer. So this algorithm, it is called as a decimation in time algorithm. Okay, in decimation in frequency algorithm, the first, that is if the given data is n point DFT, mean first n by 2 sequence is separated, next n by 2 sequence is separated. Okay, that algorithm is called as decimation in frequency algorithm. Okay, the next thing, what is the total number of complex multiplication required to compute the endpoint DFT by radix to FFT? So this FFT algorithm is otherwise called as radix to FFT. So if you want to calculate endpoint DFT using this FFT algorithm, how many number of complex multiplications are required? Means it is n by 2 log n to the base 2. This is a very important question. So already you know the advantages of the fast Fourier transform is that the computation, number of computation used to compute the DFT reduces. Okay, what is the meaning of computation reduces? Means number of multiplication, number of addition used in order to perform the DFT reduces when compared to the basic method of DFT calculation. Okay, so that basic method already we discussed in the previous video. In the previous video, we are using the formula, you know, the capital X of K formula, the DFT formula. The capital X of K equal to summation n equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n for k is from 0 to n minus 1. That method is called direct evaluation of DFT. Okay, So that is a direct evaluation. In that direct evaluation of DFT, the number of computation used is very high. So the same DFT answer is obtained by the two FFT algorithm, DIT algorithm and DIT DIF algorithm. So what are the advantages of this FFT means? Why the name is called as fast Fourier transform means here the number of multiplication, number of addition used to obtain the same DFT answer reduces when compared to that evaluation method. Okay, so number of multiplications used is the formula is that n divided by 2 log n to the base 2. It is important, log to the base 2. So here you see one more formula is there in C, but here n by 2 log n. If the base is not given means it is automatically taken as 10. So this is not a formula, log base 2n. Okay, so this is the very important question in this FFT. Okay, then the next question is what is the total number of complex addition required to compute endpoint DFT by radix to FFT? So in a previous question, number of multiplication formula is n by 2 log n to the base 2. Similarly, how many additions are required to perform this to compute the endpoint DFT means n into log n to the base 2. Okay, that is nothing but this complex addition is nothing but twice that of the complex multiplication. For example, complex multiplication is 16 means the number of complex addition is 2 into 16. That is n into log n. Number of multiplication is n by 2 log n. Here n into log n. Okay, these are all the very important formula. So using this, so there may be a chance that is a formula. So using that formula, so we may get the 2 mark question also. So here you see what is the total number of complex multiplication required to compute 8-point DFT. Okay, so here the capital N value is given as 8. Okay, so the endpoint DFT capital N value is 8. So we have to compute the complex multiplication. So already you know the number of multiplication required to compute endpoint DFT in radix to FFT algorithm. The formula is that n by 2 log n. So in this formula, you just substitute the n value. What is the n value? 8. So 8 divided by 2 log 8 to the base 2. So 8 by 2 it is 4 into log of log base 2 8. So 8 we can written as a this log 8 to the base 2 we can't calculate using calc. Okay, so we have to perform mathematically. This number 8 we have to represent in 2 to the power. So if you are representing 8 in 2 to the power, we can write 2 to the power 3. Okay. So then, you know, if you are taking this 3, then log base 2, the answer, this answer is 1. So 4 into 3, the answer is 12. So number of complex multiplication required to perform the 8-point DFT is 12. Okay. Similarly, so there may be, if the question instead of 8 point, so there may be a 16 point, 32 point, 64, 128 question will come. Okay, so this is a very important 2 mark problem in this thing. Okay, so here you should note that number of multiplication required to compute DFT by radix 2. Similarly, in previous video, we discussed the question number of multiplication required to compute DFT in direct evaluation means, so that is n squared or n into n minus 1. Okay, so you just read the question carefully and you have to answer it. Then the next question, what is the total number of complex multiplication required to compute 64-point DFT? Okay, so similar to previous problem, here the capital N value is given as 64. Okay, so you just write the formula, number of multiplication needed is n by 2 log n. So here the n value is 64. So 64 divided by 2 log 64. So 64 divided by 2, it is 32 into log of the 64, we can write it as a 2 to the power 6. Okay. So log base 2 to the power 6 can be written as 6. So 6 into 32, 192. Okay. So here, sorry, this answer is 192. So B is the answer. So 192 is the answer. Okay. Then the next one, what is the total number of complex additions required to perform the 8-point DFT. Okay. So in the question, complex multiplication required, we calculated. So here number of complex additions are required to perform the 8-point DFT. So how many additions are required to perform n-point DFT? N into log n. Okay. So 8 into log 8. This 8 can be written as 2 to the power 3. So 8 into 3, 24. So A is the answer. Okay. So this is also a question. The next one, the following butterfly diagram is used in the computation of dash. Okay, so you see this diagram. So here, this is the input x of n. This is the output capital X of k. So here the input is the first one, even indexed value, odd indexed value. Then first 2 to butterfly, then 4 butterfly, 8 butterfly is given. So this algorithm is called as decimation in time FFT, that is DIT, decimation in frequency FFT, all of the mention, none of the mention. So this diagram, it belongs to the decimation in time FFT. So already you know, in decimation in time FFT, the given X, it is divided into two sequences. One is even numbered sequence, X of 0, X of 4, X of 2, X of 6. This is the odd numbered sequence. Okay. Then output we will get in a order. This is called as decimation in decimation in time FFT. Okay, the next one, for decimation in time FFT algorithm, which of the following is true? Both input and output are in order. Both input and output are shuffled. Input is shuffled, output is in order. Input is order, output is shuffled. Input is shuffled, output is in order. So you just see in decimation in time algorithm, the input, the X of 0. Here you see the first sequence X of 0. The next sequence X of 4. The next one X of 2, X of 4, 1, 5, 3, 7. So how we are applying the input sequence to this DIT butterfly diagram? In a bit reversed order, in shuffled manner we are applying the input. And you see the output we get from this DIT algorithm is in same order. Okay. So in DIT algorithm, you have to note down that the input is in bit reversed order. We have to apply as an input. The output taken from the DIT algorithm is in the order. Okay. So for decimation in time algorithm, which one is true? Input is shuffled, output is in order. But in DIF algorithm, reverse. Input is in order, output is in bit reversed thing. Okay, so we'll see in the next question. Similarly, you see the following butterfly diagram that is used in the computation of. Okay, so you see this diagram. This is the 8-point DIF algorithm. So in DIF, you see the input sequence X of this is a 0. X of 0, X of 1, 2, 3, 4, 5, 6, 7. The input applied is in order. Output, you see the first output is X of 0. The second output is X of 4, not X of 1. So X of 2, this one. So input is in natural order, output is in bit reversed order. And here you see first 8-point butterfly, then 4-point butterfly, 2-point butterfly. Okay, so this diagram, it is belongs to the decimation in frequency FFT. Okay, this is decimation in frequency FFT algorithm. So you see in decimation in time FFT, first 2-point butterfly, 4-point, 8-point. Input is in bit reversed order, output is in natural order. Okay, but in this diagram, you see input is in order, output is in bit reversed order. First 8-point butterfly, 4-point, 2-point butterfly. So this is called as decimation in frequency FFT. The next one, for the decimation in frequency FFT algorithm, which of the following is true? Both input and output are in order. Both input and output are shuffled. Input is shuffled, output is in order. Input is in order, output is in shuffled. So D is the correct one. So you see in this diagram, the input is in order, output is in shuffled, bit reversed manner. Okay, this is in DIF. Okay, so you just remember it. In DIF, input is in order, output is in bit reversed. In DIT, DIT, decimation in time algorithm, input is in bit reversed, output is in order. The next one, the FFT algorithm is designed to perform complex operations. Yes, okay. Using this FFT algorithm, we can perform the complex operations. Okay. The next one, DIT algorithm divides the sequence into positive and negative value, even and odd sample, upper, higher and lower spectrum, small and larger sample. In DIT algorithm, so the DIT algorithm divides the input x of n into even and odd samples. Okay, so in DIT algorithm, you see the diagram. So in DIT algorithm, this is the DIT diagram. In DIT diagram, first we are splitting even indexed values. This is the odd indexed value. Even sample, odd samples are separated and we are processed. Okay, so in DIT algorithm, the even sample and odd samples are divided. Okay, then the computational procedure for decimation in frequency algorithm takes how many stages? Okay, so you see, this is the 8-point butterfly diagram. So in 8-point butterfly diagram, in order to get the 8-point DFT output, how many stages we are using? 3 stages. Okay, you see, this is the stage 1, this is the stage 2, this is the stage 3. If it is a 4-point DFT, only 2 stages we have to use. Okay. How many stages we can use in this DIF algorithm? That is the question. Okay, so how many stages used in order to perform the decimation in frequency algorithm? The standard formula is that log n to the base 2. Okay, log n to the base 2. Here n is that number of point DFT. For example, n is 8 means log 8. The log 8 can be written as log of 2 to the power 3. Okay, so log 2 to the power 3 to the base 3. So the answer is 3 stages. So for 8-point DFT, we have to use as 3 stages. Similarly, if it is a 16-point DFT mean, we have to use 4 stages and etc. So the formula is that log n to the base 2. Okay, then the next question, the FFT algorithm, the FFT computation is used in digital spectral analysis, filter simulation, pattern recognition, all of the above. Yes, the filter computation is used in digital spectral analysis, filter simulation, pattern recognition, and also correlation analysis also. So all of the above is the answer. Okay, these are all the applications of the FFT. The next one, the FFT reduces the computation time required to compute the discrete Fourier transform and improves the performance by a factor 100 or more than the direct evaluation method. So this is true or not? It's a true only. The FFT, the main advantage of the FFT is that in order to reduce the computation time, okay, it reduces the number of multiplication and the number of additions used by n by 2 log n log n. Okay, so automatically if computation reduces means what about the computation time? It is also reduces. So that's why the performance is increased by the factor 100 or more. It's a true only. Okay, then the next one, the FFT algorithm is proposed by Cooley and Turkey. Yes, it's a true. Then the next one, how many butterflies in each stage of DIT and DIF algorithm? Okay, how many butterfly in each stage? Butterfly means one cross. Okay, this is called as one butterfly. So in DIT and DIF algorithm, how many butterfly in each stage is n divided by 2. Okay, n divided by 2 butterflies we are using. Okay, so here you see this 8-point butterfly diagram. So in this 8-point butterfly diagram, you see in the first stage how many butterfly? This is one butterfly, 4 butterflies are there. In second stage also, this is one butterfly, this one is one butterfly. Okay, you see this one X is called as one butterfly. This is one butterfly, this is one butterfly. Similarly here 2 butterflies. So how many butterfly in this stage? 4 butterfly. Similarly here 1 2 3 4. So in each stage has 4 butterfly. If it is a 8-point DFT, so 8 divided by 2 is a 4. Okay, so how many butterfly are there in each stage of DIT and DIT algorithm means n divided by 2. Okay. So these are all the some of the questions about this DIT and DIF FFT algorithm. Okay. So here you should remember that how many multiplications and additions are required in order to perform the endpoint DFT in radix to FFT. Okay, an addition required is n log n. Number of multiplication required is n by 2 log n. Okay, and in DIT algorithm, input is in bit reversed order, output is in natural order. In DIF algorithm, input is in natural order, output is in bit reversed order. So how many stages means log n to the base 2 stages. And in each stage, how many butterfly means n divided by 2 butterflies. Okay. And the main aim of the FFT algorithm is why we are moving for this FFT instead of the direct evaluation DFT means in order to reduce the number of computation required and automatically in order to reduce the computation time. Okay, these are all the advantages of this fast Fourier transform. Okay, so that's why this transform, it is called as a fast Fourier transform. Okay, so thanks for watching my channel and please subscribe my channel for more videos. In the next video we will meet. If you want to learn the remaining DTSP MCQ video means I will give link in the description box, you can see. Okay, or in that discrete time signal processing playlist the videos are available, you can check. Thank you.